Welcome to another episode of Backyard Astronomy by Renato Biral. Today, I will present the Orion constellation, an easy-to-identify constellation in the night sky. When we talk about Orion, we are talking about a hunter, a character from Greek mythology. First, however, we will show what a sky that only exists in the imagination, richly illustrated and with trippy designs would look like. This is a representation from the 17th century of part of the celestial vault. And among so many illustrations, we see the one associated with the Orion constellation. I will separate it and put it in an easier way to see. However, there is a detail that almost no one talks about. Since it is a representation made in Europe, the sky is shown inverted in relation to what we see in the southern hemisphere. That is, it turns out that, here in Brazil, we see all those designs, and all those star maps, as if they were upside down. Now, I will superimpose a real star map with that illustrated representation from the 17th century. For this, I will use an app that is available in the Apple Store, which, in turn, is based on a famous celestial atlas. On the right side is a detailed representation of the Orion constellation properly adjusted to a view made from the southern hemisphere. And, on the left side, Hevelius representation. Quite different, right? So, no looking for drawings in the sky. Now, I will show the stars of the Orion constellation. But it is not worth showing the very faint ones. Instead, I will reconstruct the constellation from its main stars. We start with the famous Orion belt. Then I place the two bright stars below and the two bright stars above, and now, the three little stars that make up Orion's head. Isn't Orion a hunter? So, he has a dagger hanging on his belt, those other three stars. And now, some other stars, to complete. On the left would be those of Orion's shield. Now, I'll show the constellation of Orion among other constellations. First, I'll add some more stars. Now, some guidelines which help to characterize the constellation. Its modern border. And here, the other constellations that border the constellation of Orion: Lepus, to the south, Unicorn, on the east side, Gemini, that same one, of the zodiac signs, Taurus, look at the Hyades, in its horn, and Eridanus, the great river. And here, the celestial equator. It divides the celestial dome in half north and half south, and look how cool, as it is located in the region of the celestial equator, Orion is visible, practically, in all corners of the planet. Remember I talked about zodiac signs? If it were not daytime, month after month, you could see the sun passing through them. The path of the sun is called the ecliptic. It's also worth noting that the constellation of Orion is located practically next to the star Sirius. Sirius is the brightest star in the sky and is located in the constellation of Canis Major. There's a lot of interesting things to see in the constellation of Orion, and I'll start by highlighting some of its stars. Starting with the two brightest, the one called Betelgeuse, which, with the alpha denomination, would be the brightest. Interestingly, when you look at Betelgeuse, you can clearly see that it's a reddish star. And the one called Rigel, which is actually the brightest, despite its beta denomination. It's located up, diagonally, well, for us, here in Brazil. There's a detail about these two stars: they are huge. I'll talk about them later, but we can't forget about the stars of the Orion belt. It is common for the brightest stars to have Arabic names, although centuries ago there was an initiative to name them with Greek letters in order of brightness. Now, I will highlight some stars that are more than one, not double stars, but multiple stars. I start with the star called Sigma of Orion. It is not a weak star, and it is easy to find in the sky. And as cool as it gets, we have the star Theta 1 of Orion. In fact, both Theta 1 and Theta 2 are right in the middle of the dagger handle. So, I'll start by talking about Theta 1 of Orion, since it is part of the famous Orion Nebula. Just by looking with the naked eye, even in the middle of the city, you can see that the middle star of the dagger looks a bit strange. Looking more closely, we see that each of those little stars consists of 2 nearby stars. And, in fact, with a modest binoculars, you can clearly see that the middle stars are in the middle of a cloud, the Orion Nebula, also known as Object 42 of the 18th century Messier catalogue. The Orion Nebula is made up mainly of molecular hydrogen. But this hydrogen would not shine by itself and could not be seen. It only shines because it fluoresces from the light emitted by the multiple system Theta 1 of Orion. In the photo, you can understand why this system is known as the Trapezium. And you can also see the other star next to it, Theta 2 of Orion, which is also part of the nebula and also fluoresces this volume of gas. These stars are not ordinary stars, of those that are found everywhere. They are young, large, and very hot, called O-type stars overflowing with energy. In fact, the Orion Nebula is part of a large reservoir of molecular hydrogen in our galaxy, a place where stars are still born, including these rare young, large, and hot ones. In this Hubble telescope photo, the trapezium can barely be seen, as it appears as a blown-out glow. I'll just ask you not to take the colors shown too seriously. They are indeed real, but the human eye cannot see colors under low light conditions. In order for the trapezium to be shown properly, I made a kind of graphic art with another photo. Now, you can even see Theta 2. Look how cute it turned out. Let's talk about Orion's Sigma, the other multiple star system. In common with Theta 1, the star Sigma Orion shares its origin, the Orion Molecular Cloud Complex, a place where it has been possible to identify forming stars. This volume of gas practically occupies the entire extent of the Orion constellation. I'll just represent the Sigma Orion, because, unlike Theta 1, it is not embedded in the middle of a showy volume of gas. In fact, these stars also type O, although only a few thousand years older than those of Theta 1, ended up pushing away, with their intense emission, the clouds of molecular hydrogen, from where they originally were born. However, it is interesting that even at a distance, this star system makes shine the gas cloud against where the famous silhouette of the Horsehead Nebula stands out. This system is pretty cool because, beside it, there are 3 other stars. They are not gravitationally associated with Sigma Orion, but like other stars in their vicinity, they were all formed somewhat together. The sight of all these stars is worth it, it is very beautiful. Now, I'll identify the components of Sigma Orion. Let's make it easier to represent this system. This is component C. This one is AB, which looks like 1, but they are 2. And the last ones are components D and E. More than half of the stars do not have a companion, as is the case with our Sun. But multiple stars are rarer because they tend to form unstable associations that, over time, break apart. In this case, components A and B satisfy a stability condition rotating around each other every 170 years. In fact, it has recently been discovered that the component A is actually 2 stars that orbit each other in a period of about 143 days. Both Sigma and Theta 1 of Orion ultimately mark the location of fertile nurseries in the sky of stars, protostars, and planetary mass objects. The intention now is to talk about Betelgeuse and Rigel, the 2 brightest stars in the constellation of Orion. These stars share some characteristics in common. They are among the brightest stars in the sky. They were formed, more or less, at the same time. They are at a great distance, but above all, they are enormous, giants. However, these 2 stars are also close to their end. To talk about stellar evolution, I will have to try to provide some kind of introduction to basic astrophysics. But I promise it will be cool. We start by talking about Rigel, the 7th brightest star. Rigel actually consists of a double system, but its companion star is so much weaker that it ends up overshadowed. Betelgeuse, on the other hand, is a companionless star, but it has the detail of the variation in its brightness. There are times when it is much brighter, and times when it is dimmer. The brightness fluctuations of Betelgeuse are not noticeable to the naked eye and are somewhat irregular, but they follow a cycle with a duration of approximately 5.7 years. Even so, even at its minimum brightness, Betelgeuse stands out well in the night sky. As I have already presented, both Betelgeuse and Rigel are giant stars. In fact, they are giant and superluminous stars. This becomes clearer when we talk about their distance. In the night sky, several stars that we see as very bright are actually so because they are close. For example, Sirius, located 8.7 light-years away, is the fifth closest star to the Sun. Now, compare that with the distance to Betelgeuse, about 600 light-years, and the distance to Rigel, about 800 light-years. Note that Rigel, even though about 800 light-years away, is the seventh brightest star in the sky. And that even the reddish Betelgeuse stands high-ranked. Rigel is indeed extremely luminous, but indeed there's some few stars are even bigger and brighter. For example, Deneb, the brightest star in the constellation of Cygnus. It can be the 20th brightest star in the night sky, even though it is estimated to be about 1,600 light-years away. Well, a detail that Betelgeuse and Rigel also share, and which, in a way, is not without a morbid detail, is that these two stars are reaching the end of their lives. To talk about this, I will ask you again to remember those star nurseries we had talked about before. Stars form from the condensation of extremely rarefied gas that exists in those vast clouds. This process, although very long and erratic, results in a volume of gas that slowly begins to collapse around a center, which becomes increasingly massive. The gravitational attraction of more and more gas causes this center to increase and progressively heat up. Thus, although the gravitational collapse of the gigantic mass of gas provides a tendency of contraction, upon reaching the temperature for the onset of hydrogen atom fusion processes in the nucleus, a decisive tendency of expansion will appear. In the so-called hydrostatic equilibrium condition, these two antagonistic tendencies will forcibly find an equilibrium condition. And thus a brand new star will be born, which will continue to burn its hydrogen content for approximately 90% of its life. After that, the scarcity of hydrogen will cause the star to undergo a series of metamorphoses. Now, the question that cannot be silenced: how long does a star actually live? Answer: it will depend on the mass of gas that was aggregated during its formation process. If the process occurred in a way that allowed the gas volume to become very large before the hydrostatic equilibrium condition, we will have a large and bright star. Note that the temperature of 10 million degrees for hydrogen fusion reactions to occur is the minimum temperature. A larger star will also have a larger and hotter core. From the core, we have a gas envelope that surrounds it, an envelope that extends to a surface. In fact, when we talk about the surface temperature of a star, we are talking about the temperature of its photosphere, or a kind of boundary region, a last thickness where the incandescent gas shines. Now I will present to you the so-called Hertzsprung-Russell diagram, also HR diagram. It is so important that it is sometimes nicknamed the periodic table of stars. On its x-axis, we have the surface temperature of the star, and on its y-axis, the luminosity of the star. Since for most of their lives the stars keep burning hydrogen in their cores, the main part of diagram is named main sequence. The diagram was also divided into spectral types grouped according to different temperature ranges and also by certain characteristics of the star's spectrum. What the HR diagram represents is that the starlight output is correlated with the star surface. In the case of the main sequence, with that single detail, at this stage, the main fuel is hydrogen. Our Sun is considered a star and the main sequence have the G2 type. On the diagram, its luminosity is 1 Sun. In the case of our Sun, the surface temperature is about 5,500 degrees Celsius. It is no coincidence that the temperature of a daylight light bulb is around 5,500 degrees. On the Hertzsprung-Russell diagram, the cooler stars are designated the spectral type M. They are by far the most common, and they are even difficult to observe due to their low luminosity. In fact, for this class of stars, a luminosity between 100 to 100,000 times lower than that of our Sun is attributed. This has to do with the small size of these stars, since a smaller radius implies a smaller area for radiation. Here, I am showing the next spectral type, the K spectral type. They are cooler stars than our Sun, which have between 1/100th and half of its luminosity. Next is the G spectral type, which, as I mentioned earlier, is the spectral type of our Sun. In sequence is the F spectral type. Here we have already talked about stars up to 10 times brighter than our Sun. This alphabetical system, but not in alphabetical order, is quite strange indeed. It was developed by the Harvard College Observatory in the late 19th century. After the spectral class F, there are the type stars up to 20 times more luminous. But from there on, the more extreme stars begin. The hottest B-type stars have a luminosity of up to 5,000 times that of our Sun. And those of the O-type have a luminosity of about 15,000 times. There is a small detail, however, in this story. These luminosities refer to the part of life of these stars while they are burning hydrogen in their cores. This is no longer the case for Rigel, about 100,000 times brighter than the Sun, and not for Deneb with an estimated luminosity of 200,000 times that of our Sun. And, look here, Betelgeuse. There is only one way for a star with a surface so cold to also be so luminous. It has to be giant. Well, in common, in the case of these stars, what happened was that the hydrogen ran out in the core. It did not run out to zero, but the existing amount was no longer able to maintain the hydrostatic equilibrium condition. At first, the core did indeed shrink, but remember that the core, as it is compressed, will increase its temperature. When 100 million degrees are reached, helium fusion reactions will begin. And, as the temperature increases in the core, the gases in the envelope will be forced to move far away from the hot core, which will cause the star to increase in size. A very massive star can undergo a series of metamorphoses of this kind, but every of each one puts the star closer to its very end. Perhaps as a supernova, or perhaps as a black hole. For our Sun, after the scarcity of hydrogen, a first metamorphosis will take place when the gas compression ignites the hydrogen shell around the core, making it a giant. Only in the sequence, after this last hydrogen supply runs out, it is predicted that further compression will ignite the helium in its core, making it a supergiant. But in its very end, all that will be left will be a hot core, a kind of carbon and oxygen ash, shrunk to an absurd limit. A white dwarf. Now, I would like to show how the mass and radius of stars on the main sequence vary. In the 1910s, when the HR diagram was developed, this knowledge was nothing more than crude estimates. However, these data here were recently obtained through careful measurements. The basis of comparison is, once again, our Sun. Thus, the value of one solar mass and one solar radius are the ones that appear, highlighted, on the y-axis. Note that from B-type stars on, both mass and radius grow increasingly wild. In fact, these stars are voracious little monsters that consume hydrogen. All these extreme characteristics, gigantic core temperature and very high surface temperature, cannot result in an arrangement that will last for very long. The life of these brightest stars is doomed to be short. The estimate is that a star like our Sun lives for about 10 billion years, possibly spending about 9 billion years on the main sequence. And thus, for our Sun, half of that time has already passed. Well, just note the estimated lifetime for an O-type star. For cooler stars, this longevity time ends up being quite generous. The fact is that no K-type or M-type star has yet left the main sequence. Oh, remembering that dinosaurs roamed the face of the Earth in the Mesozoic era, which began 250 million years ago, and ended 65 million years ago, the end of the Cretaceous. But let's get back to Betelgeuse and Rigel, which the dinosaurs did not see. They have already left the main sequence and, currently, they have M and B spectral types. But, from the mass information they have, It is possible to infer that, at one time, they were flashy little monsters of the O-type. Even more frightening is their current radius. Betelgeuse's diameter is simply twice the diameter of Mars's orbit. And finally, the estimated ages. So young, yet so close to the end. I didn't want to miss a detail that we, amateur astronomers, end up noticing over time. In the night sky, the fact is that the vast majority of stars we see with the naked eye belong to the B or A categories. These stars, those in the hottest classes, such as types O, B, and A, always make up a minority. Given that stars in the cooler categories, such as types K and M, would make up the majority, the fact is that we don't even see those stars. These are stars that are 10, 100, 1000, or even 10,000 times weaker than the Sun. But it's interesting to know that there are so many white dwarfs near the Sun. Just think about how much water has gone under the bridge. There is another curious fact about the night sky. If we only consider stars that we can normally see, that is, not the very weak ones, a good fraction of them would not be on the main sequence. We would come to the conclusion that the sky is composed mainly of giants and supergiants. We end up with a false impression of being surrounded only by the larger neighbors. As I presented before, for much of the extent of the constellation Orion, there is the so-called Orion molecular cloud. Normally, in these fertile stellar nurseries, there are also a large number of type O and type B stars. In practice, these stars end up composing sparse sets called OB associations. The importance of these associations is that they signal the locations of star formation in the galaxy. And what is particularly interesting is to find type O stars in these locations, which are rare because they have a very short lifespan. And just look at the number of type O stars in Orion. So, if someone looked at this region of the sky in the age of the dinosaurs, they might have seen a much more boring and somewhat starless region. Well, let's move on to the final part of the presentation. I will present to you that the solar system is not located in the spiral arms of the Milky Way. To do this, I will start by presenting the legend of Orion and Scorpio. I agree that it could be more florid, but I have presented it in its essence. What is important is to show that the constellations Orion and Scorpio are actually on opposite sides of the sky. But if the solar system is not in the spiral arms, where is it then? At this point, I will only establish that it is between the stars of Orion and Scorpio. To broaden the discussion, I need to show how the Milky Way is seen in the night sky. First, the Milky Way is distributed across all 360 degrees of the celestial dome. But for a representation of a spherical surface, some kind of projection of a sphere onto a plane must be used. Thus, what is shown is the Milky Way projected onto a cylinder. Almost the entire night sky is in the photo. Starting with the Scorpius constellation, you can see that it is positioned in the direction of the center of the Milky Way. On the other hand, the Orion constellation is not precisely aligned with the spiral arm, but is somewhat on the opposite side of the galaxy's center, as if it were looking outward. It is not possible to see the Milky Way from above simply because we are inside it. Even if there were a rocket that could take a picture of the Milky Way from above, the photo to be transmitted would take tens of thousands of years to reach Earth. Therefore, what is left as an alternative is the insane work of an entire community of astronomers dedicated to studying and mapping the structure of our galaxy. The colorful spirals represent the best of what we understand about the structure of the spiral arms. Now you can see that the Sun is not located in the spiral arms. The Sun is located in a kind of connecting sub-branch between the Perseus and Carina Sagittarius arms. Interestingly, the name of this sub-branch is Orion Spur. To sum up, from a night sky perspective, almost everything we see is located within the circle shown. Let's be honest, you didn't imagine that the Milky Way was so big. Thank you very much for your attention. I truly hope you enjoyed the video.